Okay, good afternoon to everybody, to all the participants, to this conjoined webinar between the ELSA, the Endolaparoscopic Surgical Society of Asia, and the Japanese Surgical Society. It's a very exciting experience, and this is the first step, even though we already arranged in the past, but this is the first official step of a series of webinars that we are planning to organize together. Today I am co-chairing and co-chairing this meeting with the Professor Yoshiharu Sakai, that is the president of JSES, and the two coordinators of the workshop are Dr. Sasim Pudel from Hokkaido and Dr. Sujit Wijeratna from Singapore. So I welcome all of you. We will have this energy workshop or surgical energy or safety workshop. I think it's very important for all the surgeons to be aware of the benefit and also the, let's say, side effect or complication that we can create with the energy. Without delay, I pass the microphone, the virtual microphone, to Professor Sakai for welcome.
Well, it's my great pleasure to chair this very exciting session with Professor David Romanto. This is my first time to join such a combined meeting, and I'm very excited to have fantastic lectures and presentation from the several experts. Thank you.
Thank you, Professor Sakai. Let me share the screen, and then I will pass the microphone to Dr. Sujit to start the introduction with Dr. Sasim. Sujit?
Yeah, thanks, Prof. First of all, I welcome all of you to this joint webinar, which is conducted by ELSA as well as JSES, together with our sponsors, Olympus and Urbe. So without much delay, I would like to introduce you the speakers today. So Prof. Lamanto does not require any introduction. I'm sure all of you know him. And we have Mr. Sebastian, who will be giving you the lecture on basic principles. So he'll be replacing, I think, Mr. Jens Bettin from Germany. So myself and Sasim, Dr. Sasim Powder, he's from Hokkaido University. He has a lot of experience in this field of electrosurgery together with his colleague, Dr. Yusuke Watanabe, also from Hokkaido University. So together with Sasim and Dr. Watanabe, we'll be talking to you about the mechanisms of injury and how to prevent them, advanced bipolar and ultrasonic devices, and safety in OR, OT fires, and surgical smokes. So without just a few ground rules. So all the panelists and speakers, would like to request you to keep the microphone muted when you're not talking. And all the participants are encouraged to ask questions through there's a chat box. So please use the chat box to ask any questions. And if anybody wants to go back and look at the videos and listen to the webinar again, please join us in our ELSA YouTube channel, and you can listen to the webinar again and see all the videos as well. Those who are interested, this is live telecasted in Facebook, so please do join us. Towards the end of the session, we'll be putting out the MCQs, so you can do the MCQs online and then submit it back. There'll be 2 sessions of MCQs consisting of 20 questions. So, and once you submit the MCQs, you should be able to get an online certificate as well. Prof, next slide, please. Yeah, so this is a video from one of our sponsors, who is Urbe. Yeah, so I'll let you watch the video. Next.
containing potentially hazardous substances is generated during electrosurgical cutting and coagulation of tissue, also in cases of laser and ultrasound applications. The IES-3 smoke evacuation system is our solution for a safe and clean working environment. The IES-3 filters smoke and odors and extracts aerosol-charged air during open surgical and laparoscopic procedures. For use in the operating room, integrate the IES-3 into a VIA workstation, or use it as a standalone unit. The IES-3 is the universally suitable smoke evacuation system for hospital operating rooms, outpatient facilities, and medical practices. In combination with smoke evacuation pencils, you can cut and coagulate while simultaneously evacuating the resulting smoke. The 5-stage high-efficiency filter removes virtually all particles with diameters of 0.1 micrometers and more. Thus, this filter offers the best possible degree of safety.
Okay, so I think, Prof, we have about 163 participants already. So without much delay, so Sasim, may I invite you to conduct the webinar from here onwards? Yeah.
Yes. Thank you, Prof. I'd like to thank Professor Lomanto and Professor Sakai and Dr. Kasama for choosing safe use of electrosurgery as the first topic for JSES and BELS joint webinar. I would also thank thank Erbe and Olympus for this sponsoring this joint webinar with JSES and ELSA. First, I would like to ask Professor Lomanto to give us the brief introduction about the importance of learning about surgical energy. Professor?
Thank you, Sasim. Thank you, Sasim. Just a small introduction, some curiosity about energy and the use of energy in surgery. I'm sure that everybody aware, we are all surgeons. I don't think there is anybody that can do any procedure, maybe Professor Sakai, because it's highly skilled, without using a diathermy machine. So I think it's very important. And I must say that even the Egyptian 3,000 years ago already tried to manage some bleeding. And of course, as in energy today, the base of the energy was always the temperature and the thermal. In fact, we still call cautery. Cautery is a typical thermal specifica. But it was not a long time ago when two so-called genius, one neurosurgeon and one engineering in Boston, nearby Harvard, actually, Dr. Cushing was frustrated because of the high mortality for bleeding during neurosurgery procedure. And his good friend, William Bovey, was tried to invent something to reduce the mortality, and developed the first prototype of energy device. This is this one, very, very simple device. And they performed the first procedure in 1926. We are even not celebrating 100 years. So imagine how new it is, the energy. The interesting fact that these two guys went to Harvard because they need money. Today we have a startup unicorn, but at the time there was not that concept of innovation. And Harvard refused to buy the patent. And then ultimately, one company bought it for $1 and become a billionaire. Still today, when I travel around in some country, they say, where is the Bovey? So these people become ultra rich. Why Mr. Cushing and Mr. Bovey, they died destitute in Maine. But since after that, after Bovey, I think there was a lot of development with bipolar energy by Mallis, and also other form of energy in terms of laser, CO2, especially for flexible endoscopy using neodymium YAG laser. And today we also have ultrasonic devices, bipolar device, and also combined device. They use high frequency energy. There is a success and defeat. Maybe Professor Sakai doesn't remember, but one time JSES asked me to talk about complication in energy during the annual conference, and I was talking about the success and defeat of surgical energy. Yes, they are very good in hemostasis, in ablation, sealing, precision cutting, but also they are responsible of any damage in OR, like OR fires, injury. Sometimes bowel leak are due to the misuse of energy, interference with the other medical device like pacemaker, and also create surgical smoke. You see from the beautiful video from Herbe, our surgical smoke are very harmful. And I must say today, I don't do any procedure without surgical smoke aspirator, and because it's much healthy and less smelly. But what was dramatic and why we are running this course also, we start to do this quite routinely since 5-6 years ago, because different survey, this is a very old one, 20 years ago, show that everybody experienced some complication from electrosurgical, from surgical energy. And at least 70% knew of a personal experience of damage. And also, we can see that most of this complication happen because we are not trained in it. We can see how most of the surgeons have less than 1 hour training, or 70% less than 1 hour training. So we will lack in this energy. That's why many residency programs today involve surgical energy. And that's why also the American Society started fundamental use of surgical energy program in 2011, probably because they understand that there was a need to fill with the necessity to create a course, a proper course about energy. So inadequate training. And the first question that come in mind, do anybody allow yourself to operate as or somebody to doesn't know anybody, doesn't know anything, or haven't received any formal training on energy? It's the same as driving a car without a proper license. So we need to understand the basic principle of energy to make not only the better use of it, but also to avoid injury. So be safe, be healthy, because in terms of pandemic, we also need to be healthy and enjoy the course. Thank you. Thank you very much.
Thank you, Professor Lomento, for giving us a brief overview of why we need to learn about surgical energy. Now we'll pass on the mic to Mr. Sebastian, who will be talking about the basic principle of electrosurgery. Sebastian, you have the video ready?
Yes, thank you also for the invitation. I'm sitting in for our team leader, Mr. Jens Bettin, and I'm going to play a recorded video for you. Excuse me if the sound quality should be too low. Please simply turn off your mics or your sound speakers. I'll share the video now, and then we are ready to go.
Even though electrosurgery is one of the most common surgical technologies, it might also be one of the most misunderstood. Please join me and learn more about the functional principles of this technology and its sometimes not so intuitively understandable effects, and why misuse may lead to patient risk. I'm Jens Bettin, team manager of Airman Academy at the headquarters of Airman in Germany. Thank you very much for having me as speaker and for letting me be part of the SEnSOR course program on ELSA and JSES. Please accept my apologies for not speaking live to you today. I therefore very much appreciate that I was allowed to present with this recording. Now, the use of electrosurgery
serves to perform surgical treatment by cutting and coagulating with electricity. For coagulation, the tissue is heated by the electric current. The heating results in a shrinkage of the tissue and a denaturation of the proteins. Both processes cause the desired hemostatic effect. The advantage of applying electric current is that it can technically be dosed very well. Depending on the selected settings, the current can heat up the tissue almost instantly to several hundred degrees Celsius. At this high temperature, the tissue vaporizes at the point of contact. This serves to cut and dissect the tissue. The lateral heat spread that comes with the cut adds additional coagulation. This also helps to minimize bleeding. The intensity of the lateral coagulation depends on the settings that I will explain later. Most often it is believed that the heat comes from the instrument and that electrosurgical instruments are nothing else than an electrocautery. Couters are hot instruments, and its hot snare will cause the tissue effect. The problem of these instruments is that when the snare gets in contact with the tissue cools the snare almost instantly, and the effect is therefore rather short and very weak. Let me explain in which way electrosurgical instruments work differently than such a cauter. Here you see an electrosurgical electrode in an infrared animation. The dark blue of the background is a tissue sample that for this experiment replaces the patient body. Both the electrode in the front and the tissue sample are blue. That means they have almost the same temperature. The electrode is now already activated. You see that in contrast to a cauter, it does not become hot. Now I closed the electric circuit by touching the tissue, and now the tissue at the point of contact becomes hot. Note that the electrode itself only indirectly became hot. The rear part of the spatula is obviously still cool. Let me show you the animation once again. This proves and shows that the functional principles of an electrosurgical instrument is different from a cauter. Here, the current flows through the patient and the tissue is intrinsically heated. That means that the current develops the heat inside the tissue, not from the exterior. The temperature and tissue effect, though, does not only depend on the technology and the selected settings, it also depends on other factors, the size of the electrode, even in part also of the patient. But you as a surgeon also have control of one of the most important influencing factors, and that's the time. It means how long you activate and how fast you move the instrument, but also how big you make the contact of the instrument. Physically, the current is generated by voltage. Voltage is kind of a force that acts on charged particles like ions and electrons that then flow through a conductor. These flowing particles hit against the atoms. This lets the atoms vibrate. This vibration of the atoms is basically the thermal energy that we can sense and measure as temperature. The higher the voltage, the more current is produced and the hotter the material becomes. The electric current can only develop when an electric circuit is closed. In case of electrosurgery, the patient becomes part of the electric circuit that is closed by the instrument and a second electrode, the so-called neutral electrode. The required temperature, though, may only develop at the point of contact of the instrument. So how is it possible to determine the exact place where the heat develops? This is actually determined by the current density. As you can see in this animation, the heat only develops where the charged particles are sort of squeezed through a thin constriction. This is where the current density becomes high and thereby the temperature becomes high. Note that this happens wherever there is a constriction within the electric circuit. Now, in case of a monopolar instrument, the second electrode therefore has a large contact surface to ensure that the current density remains low. So the name neutral electrode comes from the idea that its temperature shall remain neutral. Very often it is believed that the neutral electrode serves to ground the patient. Actually, it does the opposite, and you should do everything to prevent the grounding of the patient and electrically insulate the patient to prevent leakage currents. As you see, the current flows through the patient, but the electric path is not necessarily straight as the current follows the path of least resistance. The resistance depends on the type of tissue. Fatty tissue and dry coagulated tissue have higher resistance than blood and muscle tissue, for example. Also, the diameter and the length of the current path have an impact on the resistance. Therefore, the current will mostly flow across the conditions shown above on this graph and less across the conditions shown below, where low conductivity, small diameter, and a longer path make it harder, more difficult for the current to flow. Bipolar instruments use the same principle of current density. The difference is that they have an integrated second electrode and do not require a neutral electrode. Still, the patient needs to be part of the electric circuit, just that the electric path now is much shorter. Now, what are the influencing factors on the temperature and on the resulting tissue effect? As the law of Joule heating shows, the temperature depends on the intensity of the electric current, the resistance, and how long the instrument is activated. To make it less mathematical, the more current is used, the smaller the diameter, the lower the conductivity of the tissue, and the longer the instrument is activated, the hotter the tissue becomes. To heat up the tissue effectively, the current must be high enough. Electric current, though, can be very dangerous, as it usually causes neuromuscular stimulation. And this is true for direct current, DC, but even more for alternating current, AC. The reason why the patient is not electrocuted is that electrosurgical generators use alternating current with high frequency. As the graph shows, the most dangerous frequency is somewhere around 100 to 1000 hertz. With much higher frequency, the intensity of the neuromuscular stimulation becomes weaker, because with higher frequency, the cycles of the alternating current become so short that our nervous system cannot sense the current anymore. By standard, the used frequency must be at least 200,000 hertz or higher for patient safety. The frequency itself has almost no impact on the tissue effect. The type and intensity of the tissue effect is controlled by the selectable settings. Typically, electrosurgical units have so-called modes to select from. With the mode, you basically select a certain type of tissue effect. The yellow button activates rather sharp cutting modes like auto cut, or sort of a blended cut with an intensive coagulation seam like the dry cut. The blue button activates coagulation modes like soft coag that will produce a sort of boiling effect, or forced coag that will make a rather fast and dry coagulation. Spray coag, and especially argon plasma coagulation, will produce longer sparks that can be used for fast and broad coagulation with less penetration depth. When you look closely to the tip of an electrode, you will often see such sparks not only on spray coag and argon plasma coagulation. They actually play a very important role in electrosurgery for most monopolar modes. Because for cutting, the current density produced by the contact of the electrode is not even high enough. The required high temperature comes from these sparks that form when the voltage is somewhat higher than 200 volts. These sparks are like thousands of tiny, very thin needles, and they cause a very pinpointed vaporization of the tissue. This is actually where the cutting effect comes from. With even higher voltage, this effect becomes even stronger. This graph shows these modes in comparison. Soft coag uses a maximum of 200 volts, resulting in desiccation and blood clotting. This rather lower voltage will not create sparks and no cutting effect. Autocut uses higher voltage that produces sparks, and therefore it is a cut mode. But also coagulation modes like forced coag make use of sparks to produce a faster and drier coagulation than, for instance, soft coag. And they use even higher voltage. Usually this would lead to an even sharper cut than with an autocut. But as you see in the graph, forced coag is modulated. That means that the high peak voltage is not applied constantly. It is sort of pulsed. And this minimizes the cutting effect of these sparks. And when the pulse is made longer, the effect becomes more cutting again, like with such a blend cut that we call dry cut. This serves to achieve a more intensive coagulation seam than with the unmodulated autocut. And lastly, the spray coag uses extreme peak voltage of several thousand volts to produce these longer sparks for a short sort of brush effect. To prevent it from cutting, these high voltage modes are highly modulated. That means the pulse is very, very short. Technically, the modulation of such modes is given with the duty cycle or the crest factor. You can select from these modes depending on the required hemostatic effect or the cut sharpness, or if it shall be rather pinpointed or have a broader and more superficial coagulation effect, or on the contrary, a rather deep and ablating effect. But it can also simply depend on your preferred way of work. Depending on the electrosurgical unit, there can be several options. A technical limitation, though, comes from the maximum voltage that the instrument and its installation can tolerate. This is an advantage of monopolar instruments, as they can be used with much higher voltage than bipolar instruments. Another type of advanced electrosurgical technology are thermofusion and vessel sealing modes and instruments. While regular coagulation modes are rather used for capillary bleeding and on smaller vessels, thermofusion and vessel sealing modes are designed to seal larger vessels. The vessel walls are compressed by the jaws of the instrument. The compression is very important for the effectiveness of the seal. With the start of activation, the generator will measure the electrical characteristics of the tissue and perform a technically controlled coagulation that results in a thermal seal of the vessel. This is not only about the generator's control technology, also the instruments have to be specially designed for vessel sealing. Control technology is not only required for these special modes, also the regular modes must be controlled. Otherwise, the changing conditions would lead to a chaotic and uncontrolled tissue effect. Depending on the type of generator, typically either the electric power or the voltage is controlled. Ampere units have a constant voltage control. This helps to keep the tissue effect consistent. To increase or reduce the intensity of the selected mode, voltage control units let you select higher or lower voltage by adjusting the so-called effect. With high effect numbers, the peak voltage is higher, the tissue effect thereby becomes intensified. Note that some units also have a power limitation to select from. This is sometimes misunderstood as power setting. As this graph shows, the electric power on such a voltage control device is a curve. With the power limitation, the red line, you can prevent excessive current, for instance, when the resistance is extremely low. Usually, these settings do not need to be adjusted all of the time unless it has been set too low and the tissue effect thereby becomes too weak. Make sure to know which type of electrosurgical unit you're using, because other units might have a power control where you cannot set the peak voltage, but the resulting electric power. The settings are definitely not the same and cannot directly be compared. You can identify these units by the unit of their settings. If they say watts, it is a power control unit. If they say effect with the unit volts and max watts for the power limitation, it is a voltage controlled unit. The other lectures today will discuss insulation failures, capacitive coupling, fires, and possible risks of misuse in detail. Therefore, these pictures shall only be an introduction to these important topics. So please be aware that incorrect use of electrosurgery can lead to high current density at other parts of the patient body, can damage active implants, and that the spark formation can ignite flammable gases and cause fires in the operating room. All these risks are well known and published. A good and reliable source of reference and guidance is this technical report by the International Electrotechnical Commission. As you see, even though electrosurgery is one of the most used surgical technologies and known for almost a century now, it must be well understood and educated. If you wish to learn more about the functional principles and safe use, I invite you to take our comprehensive e-learning course or to attend one of our online trainings on our learning platform, www.academy.erbe-med.com. This brings me to the end of my lecture. Let me thank you very, very much for your attention. Again, I'm sorry that I could not speak live to you today. Greetings and best wishes to all of you from Germany.
Thank you, Jens, and thank you, Sebastian, for standing for Jens. It was a nice and very informative topic about giving us the basic of electrosurgery. Now we move to next topic. Our colleagues, Dr. Sujit, will be talking about the mechanisms of injury and how to avoid them. And then I will talk, and this is a very important topic, so we are dividing our work here. So he will be giving the lecture, and I'll be showing some live demonstration and some videos. Sujit, can you start?
Yeah, thanks, Sasi. Can you see my screen?
Yes, we can see.
Okay, great. So the usual monopolar electrosurgery we use, there are a few sites injury can happen. So one is the dispersive electrode. So during the dispersive electrode, there can be application site issues, which we will talk about. We will be talking to you about in a short while. There can be partial detachment. The current electrosurgical units are actually capable of detecting most of these dispersive electrode issues. So it doesn't allow you to use the active electrode if there's an issue with the dispersive electrode. So most of the new ESUs are equipped with this function. Then there's active electrode injury, which could be an inadvertent activation, or it could be a direct extension, which we will show you some videos later. Then there's current diversion. This is interesting. So you will also see some videos about current diversion and insulation failure, direct coupling, capacity coupling, and alternate site injuries. So let's talk about them in detail. So when you apply dispersive electrode, there's a few things that you must look for. Patients' skin if the skin has a lot of hair, there's a chance that air may be trapped in between. When you apply the dispersive electrode, there may be a chance that air can be trapped between the hair follicles, as well as if you don't uniformly apply the dispersive electrode, there's a chance that you may get some air trapped within the dispersive electrode, even without hair. Then the other thing is you should make sure that the surface is dry, and you should not apply a dispersive electrode over if the patient had a hip surgery, you should not apply the dispersive electrode just over the previous hip surgery scar, because you're going to have a metal there, and then and it's going to affect the routine completion of the current or the energy. So partial detachment, as I told you, most of the new ESUs are able to recognize this issue, so should not have a problem. But to keep an eye on most of these dispersive electrode issues, so that you can prevent any inadvertent injury to the patient.
Okay.
Yeah, Sasim, up to you. I will stop.
Okay. So you stop sharing and I can. Okay. So I'm showing you what can happen. So this is sort of in this like James, Mr. James said in lecture, dispersive electrode is actually a second electrode. So what happens is that, so you can see my video, right?
Yes, can see you.
Yeah. Okay, so if the it does not burn because the area of attachment is high, what happens if it's very less like this? There can be burn at the site of attachment. So we are just doing an experiment here, so showing that like there can be a burn at the site of if it's not properly placed. So like Sujit said, a lot of these new machines, and they don't allow for this to happen. So I can show you the videos. I have here, so I have a chicken here on the dispersive electrode. So if I try to take it out, like it will just go on like I cannot hear it, but it gives us the warning sign. And then if I try to use my active electrode on this, it will not work. It will give the warning sign. So most of the new machines, they have a sort of fail-safe check, but older machines do not have these. So you need to, if you're holding like earlier generation machines, you have to be very careful of where you place your dispersive electrode, and make sure that it does not get detached, because it's a second electrode. There is electricity there, and you can get burned there. Okay, that's all I have. Like, we can go to the next one.
Thanks, Sasim. So we're gonna have this like an interactive session because it's an important topic. So let's move to the next slide. Sasim, can you see my?
Yes, I can see your slide.
Okay. So insulation failure. So this is an issue with current diversion. So many surgeons routinely use the coagulation waveform, and there are new machines available to check the insulation of our endoelectroscopic instruments. But if these new machines are not available in certain places, you must look for the integrity of the insulation of your electroscopic instruments. So why I say that is because, as you can see here, so if this surgeon is using this at a targeted site, but if the insulation is not intact, the current will find another pathway to leak it out and then get it back into the ESU. So this way, there can be thermal injury to bowel, or it could be any other organ, which you may not even see. So this is an important thing that we should look for, especially in institutions or and places where they do not have these new machines which can check properly for insulation failure. So also usage of high voltage during usage of monopolar instruments, it weakens the insulation. So breaks in insulation can create an alternate route for the current to flow. And if this current is concentrated, as I told you earlier, it can cause significant injury. The incidence, so about 226 laparoscopic instruments were tested in one of the studies, and insulation failure occurred more often in reusable instruments. We all use reusable instruments, and most of our endolaparoscopic equipment are actually reusable. In the reusable sets, when they evaluated them, 71% were found to have at least one instrument with insulation failure. And this insulation failure was more common in the distal third of the instruments compared to the middle or the proximal third. So this is one of those machines that, that can be used to see whether an instrument is safe to be used if the insulation is intact of those endolaparoscopic instruments. So if it is not, if it passes, then we continue to reuse this. If not, then we need to look for other alternatives or send for repair. Sasim, up to you.
Okay, so can you just stop the sharing slides here? So here I have one instrument here. So this has an insulation failure. So look, what happens is, like, if I activate it, so here it's not supposed to burn here, but because there is failure, it will burn here. So, but what happens is our eyes are generally on this side, at the tip of the here, and you never know if it was touching bowel, and then like you may have a bowel leakage afterwards, and you never knew, like, and you check for the videos again and again, and then you don't know how the bowel leakage happened. But if you have insulation, smaller breaks can actually cause larger damage. So how do you check? I have with me here insulation, one type of insulation. And this is like a device. It's a very small device, but if you just go here, like the tip of the here, it's okay. So it's right, and then I just have with these. So I just need to put it here. So it's at the when there is insulation failure, it gives the sound. So very old instrument. And then like when there is no insulation failure and the normal part, it does not make any sound. So these so with this, it's very important, like Dr. Sujit said, it's very important to regularly check your instruments for the insulation failure so that you don't have the accidents like the ones Dr. Sujit talked about. Over to you, Sujit.
Okay. Okay, so we move on. So next, I think we will talk about the other current diversion issues. So one is direct coupling. So direct coupling, I show you this video. we do use it in usual practice. So if there's any bleeding, if we grab it with a forceps and then we ask our assistant to touch it with the coagulation, or we ask the assistant to touch it with the cup mode. So in order to achieve a good coagulation. So this in fact is actually direct coupling, but this is when we know what is happening. But direct coupling can happen when we do not know and we do not see. And this is where injuries can happen. So when we use a monopolar diatomy, and then if the active electrode is in very close to your camera or another metal instrument, there is a chance that the current may leak out, and then wherever the not intended instrument is touching, that it can cause a thermal injury. So this is essentially direct coupling. So if I show you this video, so this is basically direct coupling. This is, we know what is happening in front of our eyes, but the important thing is if there's an instrument which is closer to your active electrode, and if you are not seeing it, if there's any bowel closer to this area, it can get damaged. So this is a mechanism of injury, and this is what we call direct coupling. So capacity coupling. Capacity coupling usually occurs when current or energy is built up between two conductors separated by an insulator. So this can happen usually in mixed metal and plastic trocar. If it's an all metal trocar, and if you activate it without touching an organ or even a targeted tissue, what can happen is charge can build up without completing the circuit. So if you use an all metal trocar, as shown on the picture here on the left side, the metal actually can conduct this stored energy into the abdomen or wherever the metal trocar is in contact with, and it will help to complete the circuit. But in mixed metal and plastic trocar, so this stored energy between the two conductors may not have a pathway to get into the ESU to complete the circuit. So this is where capacity coupling can happen. So this is more, the chance of this happening is more in longer instruments where the insulation is thin, where you have a high voltage, where you use high energy. And when you use narrow trocar, as well as when you use open circuit activation without activating at a target organ. So this is very important because this is a poorly understood area. So because of that, we need to keep this in mind. So Sasim, I leave it to you to show the video for this part. Sasim?
Okay, yeah, I was muted. So here I have a tube light and a simple pencil body. So one of the ways to increase capacitive coupling is like when you like just roll around it, wrap around it. What happens is the inside this wire, the plastic insulation, there is a metal wire. And this you have an insulation here, and the tube light has a conductor. So when you have two conductors being separated by one insulator, and then in these type of cases, like this is where the capacitive coupling occurs. So the current can jump from, like, to put it very simply, the current can jump from the inside wire to the conductor. So when I activate, it just lights up, right? So this means that when you are wrapping around this here, like the current is getting built up inside here. So one of the practical examples, what we can show it, what happens when, like a lot of people I see doing is like we have like these sort of clamps. Like a lot of people, like they just love to wrap the metal wires around these clamps, right? But when you are doing this, you must remember that you are also like causing the electricity to build up here. So I'll show you like exactly what happens with, let me change the camera. So we go back to chicken. So when we activate it, okay. So you could see the spark. So like actually like the it is okay. So if it's okay, just a minute. So with the whenever if you are like touching the patient just a bit while you are wrapping it, so there is a recipe for disaster. You can burn the patient at the site of application of where you're putting clamps. So we suggest that you should never do that. Bringing different metal cords together all can also increase sort of this sort of things. So this was one practical example that can happen in everyday OT. Over to you, Sujit.
Yeah, thanks. Okay, so to conclude this part, so I think we need to talk about active electrode site injury as well. So sometimes when we are doing a procedure, we are not looking at where our active electrode is. And then there is a chance that we may accidentally press either the coagulation mode or the cup mode with the foot pedal without looking at where the active electrode is touching. And this is where inadvertent activation can happen, and which can result in tissue injury. So this has to be kept in mind. So how to avoid these undesirable effects, or how to avoid injury during electrosurgery? So firstly, most of these potential problems can be avoided by following some of these. So always inspect for insulation carefully, and as how Sasim showed it to you, if the equipment are available to test for insulation, please do use them. Use the lowest possible power setting. Use a low voltage waveform, such as a cut mode, and use less energy. So use brief intermittent activation versus prolonged activation, and do not activate in open circuit. Do not activate in close proximity or direct contact with another instrument. If possible, bipolar is a safe way of using energy. So if you do have the instruments, such as, so ERBI do have the bisect, biclamp, there are other bipolar instruments that are available. I think Sasim is going to talk to you in detail next. Then select all metal or all plastic cannula systems, but do not use those mixed cannula systems, which can result or which can predispose to capacitive coupling. So as I said, so utilize available alternatives like high frequency bipolar, ultrasonic, or reusable bipolar instruments. Precaution with pacemakers and defibrillators. So do not bundle cords of multiple instruments together. This is what Sasim showed you. So place unused devices in an insulated holster, so it's actually safe. So I got nothing much to say beyond this. So for mechanism of injury and how to prevent, Sasim, can I pass over to you to start with the next lecture, which is about high frequency bipolar as well as ultrasonic.
Okay.
Thanks. I will stop here.
Okay. Thank you, Sujit, for the wonderful presentation. I think it's a very important topic that we're talking about here, like how to avoid injury. So I'll move to the next presentation. I'll be talking about advanced bipolar and ultrasonic devices. Okay. So in this session, we'll be going through this following topic. First, I'll talk about advanced bipolar, and then like pros and cons of ultrasonic of advanced bipolar, and then I'll talk about ultrasonic devices, and we'll talk briefly about residual heat and lateral spread and best practices about these machines. And Dr. Sujit will be showing us some videos. So first, we talk about advanced bipolar. So when we talk about advanced bipolar vessel sealing system, I think one of the Ligatio is what it comes immediately to my mind. But there are various other devices like that can be categorized as advanced bipolars, like bisect and biclamp. So like Mr. James talked briefly about differences between monopolar and bipolar devices. So this is just a review slide. So in monopolar, what we have is you get the electricity from the active electrode to the dispersive electrode. It travels through the patient. But in bipolar devices, what you have is you have two active electrodes in the same instrument. So the electricity is traveling back and forth between that two electrodes. So it does not get to travel much further inside the patient. So when the tissue or vessel is pressed together by the jaws of bipolar instrument, or we compressed, or what we can say coax the tissue, most of the bipolar, they used low voltage wave. So this is basically a pure cut wave, a continuous current. And this gives us more gradual and even coagulation, and resulting in a very nice and homogeneous closure, right? So with the advanced bipolar, what we have is a smart generator technique that receives the real-time impedance feedback from the tissue and controls how much current and power that is going through the active electrode. So to give us the very good coagulation. So it also has a pulsating energy delivery system, so that the electrode does not get overheated. So it is designed in such a way that it tends to keep the temperature of the tissue between 60 to 80 degrees Celsius. It rarely gets above 80 degrees Celsius. This is very beautiful. This is the ideal setting to do the coagulation. So, and most of these devices also have audible signal indicating that the adequate coagulation have happened, so that users don't overuse it. And there are pros and cons of these devices. Since it's a bipolar device, it does not use any dispersive electrode. So current does not flow through the body of the patient. So there is, it also, as I said, it uses less voltage. Most of these devices uses less than 200, around 200 volts or less than that. And it has ability to seal up to 7mm vessels. But you have to remember that these machines, they also have lateral thermal spread, 1 to 3mm, that I'll talk about a bit later, and Dr. Sujit will be showing video. And there is a chance of current limits through the cord. It's because the current voltage is very low, this chances is very minimal, but it's not zero, but it's much less than what you have in the monopolar. And obviously, like most of these devices cost more than your normal monopolar instruments. Next, I move to ultrasonic devices. So what we have, ultrasound is radio frequency is the wave for electromagnetic wave. When it's above some frequency, we call it radio frequency wave. Ultrasonic wave is for the mechanical wave. So of anything above 20,000 hertz, we call ultrasonic waves. So this is the sound that we cannot hear. So above 1 million to 30 million hertz is what we use for diagnostic ultrasonography. In surgery, we generally use the wave, ultrasonic wave from 20,000 to 60,000 kilohertz. So what happens in the ultrasonic devices? So this generator we have is basically similar to like electrosurgical unit. They takes our electricity from the wall, that is 50 to 60 hertz depending on the country, and it changes it to ultrasonic frequency of 20,000 to 55,000 hertz, depends on the machines that various companies use. So these high frequency waves, what they do is they travel to the handpiece, and in handpiece they have a piezoelectric disc that convert the electrical energy that comes with to the mechanical energy of the same frequency. So 23,000 to 55,000, depending on the machine you are using. So, and this is then transferred to the shaft where it is amplified and then transferred to the active blades, which causes the vibration. It goes back, the active blade goes back and forth like it's 50 to 100 micromillimeters. So it's a very minute going back and forth movement of the active blade that happens at the frequency of 22,000 to 55,000 per second. So this helps us do the cutting, cut the tissue, coagulate the tissue, or aspirate it. Okay. So what happens is, in the simple summary, so it causes effect in few things, right? So because there's a vibration there, it causes friction and heating. Heat is one of the obvious things that happens, right? So because there is a friction between active blade and tissue pad. So this heat causes tissue effect similar to the monopolar coagulation. And besides that, there is some mechanical disruption because the jaw is going back and forth at a very high speed, right? So this mechanical dispersion helps the cut through the tissue. This is not something that you get in the monopolar instrument. And besides that, you also have the effect called cavitation. So it occurs when you actually get vaporization of the tissue of the ultrasonic scalpel, and it generates a lot of spray. That's what you see, the spray and the mist, right? And besides that, at the tip of the active blade, it's actually going back and forth at a very high speed. So you also have a drilling effect. So you have to make sure that it is not like the tip of the instrument, active blade is not touching any vital organs like blood vessels. It can actually puncture a hole there. And basically, there are two settings you use in ultrasonic devices. A lot of these machines can control the more than two settings. Like there is settings in maximum and minimum. So maximum and minimum. Also, you can like make minute changes. So basically, what you are controlling is controlling how much the distance the active blade travels while you're going this back and forth movement. So in max settings, so active blades protrudes more. So it has a longer stroke, and that makes cutting easier. So you can think of it as you are holding a saw cutting wood. So you are going back and forth, making longer stroke, right? So while the cutting is faster, so there is less hemostasis and less time for lateral spread. Whereas in the minimal setting, you have the similar frequency, but the protrusion is much smaller. So you are just going very small length. So it takes time to cut. But on the other hand, you can have more time to have a hemostasis. So it gives a very good hemostasis. And there is longer time to give the collateral thermal injury. So one thing you need to consider is that there is a lot of user-dependent technique while using these devices. So operator needs to make an intraoperative decision on which button you are pressing in each situation. If you are going very small, like you are just cutting through the omentum, like without any blood, you could just go with the max button. If you are coagulating you need to coagulate some blood vessels, you go for max, minimum, min setting, minimum, min button. On the other hand, like so basically it is a trade-off between cutting efficiency and coagulation efficiency. And besides the button you choose, you can also influence the efficiency of tissue cutting by how tightly you squeeze the handle. So how tightly the active blade is sitting on the tissue pad, or whether you're lifting the tissue or applying the tension on the tissue. So pros and cons, like ultrasonic device is a very versatile device. It can seal up to, historically it's sealed up to 5 millimeters, but newer devices, they can seal up to 5 millimeters. So there is a minimal spread of energy through the patient body. There is no smoke. There is a mist and spray, but there is no smoke. And one of the biggest advantages is there is no electricity in the patient. So electricity just stops at the handpiece, and after that is all mechanical energy. So you don't need any dispersive electrode. You don't have the risk of current diversion. So there is no interference with echocardiogram or pacemakers or any implanted devices that you have. On the other hand, like the biggest drawback of these devices is it has a very high residual heat. So, and I think lateral thermal spread is depends on the setting you use. And it's but there is a lateral thermal spread of 1 to 3 millimeter, and sealing quality depends on the technique that you use. And there is a mist formation that often like blurs the vision, and obviously it is more expensive than your normal monopolar devices. So I was talking about residual heat. So I'm comparing here the ultrasonic and the bipolar, advanced bipolar. With the ultrasonic devices, the temperature can rise up to 200 degrees Celsius, sometimes more. With the bipolar, it rarely goes above 80 degrees Celsius. So it's much more hotter. So there was a study done in 2011, and like it showed, like it compared the residual heat of different instruments and like time it takes to cool off. So even after, you can see in the graph here that even after 20 seconds after activation, the baseline temperature of the ultrasonic devices was still more than 20 degrees Celsius above their baseline. So it was still hot. So, and it's highest with the ultrasonic devices, and it is lowest in the advanced bipolar. So it can cause significant tissue injury. And the safety measure is you need to carefully activate the device under direct visualization. Make sure that you see where the active electrode is all the time when you're activating, and do not manipulate or dissect the tissue without allowing the active blade to cool. So Dr. Sujit has some videos showing the residual heat and lateral spray. I'm going to stop sharing my screen. Okay, so Dr. Sujit.
Are you able to see my screen?
Yes.
Yeah. Okay. So what you see here is a combined device which uses both ultrasonic as well as high frequency bipolar. So this is called Thunderbit. It's by Olympus. So you have two main buttons to use. So your ultrasonic energy is used here for the seal and cut, and for pure seal, we use advanced high frequency bipolar. So this is the Joule, that is the oscillating Joule. And then for bipolar, there's a metal component here, so that will complete the tissue effect at the desired tissue for bipolar energy. So if you need to use cut and seal at the same time, we use the pink color button. So you can see the tissue effect here. So it does cause some lateral damage. Okay, it does produce some mist. So this part is important. So it produces the mist, and then you can see the amount of energy that it uses. Okay, so this is without activating. You can see how much of tissue damage can occur. So this is due to the residual heat. And you can see the amount of lateral thermal damage. And if we see this in an infrared camera, you should be able to see how far it spreads. So this is where I'm using ultrasonic energy. So cutting and sealing at the same time. So you can see the amount of thermal damage that has happened. So this is without activation. You can see the amount of residual heat that this contains to burn the tissue. Okay, so next I think we will look at the bipolar instrument. So I'm using a ligature to demonstrate this part. So this has two metal electrodes to complete the bipolar circuit. So that's the activation button when you grab tissue. This button will activate the circuit, activate the unit, and it will deliver energy into the tissue. So in bipolar, this does not have a separate cutting mechanism. So you use mechanical blade to do the cutting. You can see compared to the ultrasonic, the amount of lateral thermal damage, the residual heat. So this is ultrasonic and this is bipolar. So the thermal damage seems to be slightly less in bipolar. It does have continuous feedback, at least about 200 times per second into the machine about tissue impedance. So this is how it recognizes. So this is without cutting. You can see the amount of tissue damage. Yeah, I think Sasim, that's all I've got to say. So
okay, so
yeah, we do have a lot of these energy devices in the market, and they do have certain recommendations. So, but ultimately, using the available evidence, and it's up to the surgeon who should decide what is safe and what is not. So I'll leave it to you to invite.
okay. Yeah, okay. I'll just finish off with the. I have a like we just finish off with the best practice. So this is sort of summary slide. So for the advanced bipolar, you need to. I think it's best to clean the inside of jaws frequently so that it does not have anything trapped. So you have a nice seal. And for advanced bipolar, it is better to have a tension free. So if you want to have a full seal, it's better to use it tension free. And if there is an anatomical tension or large vessels, it's also good to have an overlap seal. So you seal it more than once before you fire that mechanical knife to cut. And avoid capsular of tissue at the hinge of jaw at the bottom. So that's where you clean it, because it won't seal properly there. And like the knife, if you are using it over the clips or staple to cut the suture, it can damage it. So be careful not to use there. And always consider like the lateral thermal spread, so 1 to 3 millimeters. So you need to have that margin of error. So if you are using very close to very important organs, it can damage those organs, right? So, and one thing to remember is it's said that it can work up to 7 millimeter blood vessels, but if it's calcified or diabetic blood vessels, it may not work very well. So you need to be careful on that. On ultrasonic devices, the best, I cannot report it more often. This is very important thing. You need to allow for cooling period for manipulation of tissue. Remember that active blade gets extremely hot. It can go well over 200 degrees Celsius. And careful activation of device until direct visualization. You need to see where your active blade is, and account for drilling effect of the tip, and also lateral thermal spread, as Dr. Sudhit showed. And ultimately, you need to choose your setting according to your needs. So if you are using the max button, it's a faster cutting, less hemostasis, and less thermal spread. Min button, slower cutting, better hemostasis, more thermal spread. So you need to choose it carefully and wise. So this is all we have. So just a reminder that ELSA is currently doing a life membership for $150. So those of you who haven't been member, please use this opportunity. So after this, I pass on the mic to Dr. Watanabe. He is well known in all over Japan. So whenever the topic of safety in this energy devices and safety comes, Dr. Watanabe is the first person like everybody remembers in Japan. So he has done well over hundreds of these sort of hands-on courses well over Japan. So he is here to talk about OR fire and surgical smoke and finish off our lecture session. Dr. Watanabe.
Thank you for introduction, Sashim. Good afternoon and good evening, everyone. I'd like to thank you for giving me the chance to speak here. Before my talk, let me just start by introducing myself. I am a GI-MIS surgeon. I'm currently involved in the JSES International Committee and SENSOR Fundamental Use of Surgical Energy Fields Committees. In my presentation, I'm hoping to give you a quick overview of oral fires and the surgical smoke. Firstly, oral fires, focusing on how to prevent the fires and how to respond to oral fires. This is the artificial fires. For preventing oral fires, we must understand oral fires. Oral fires are rare, but they're devastating events which remains an underreported source of surgical complications. We all have heard about fires in the OR, but there's no clear data regarding how many really occur. There are around 550 to 650 cases that are reported in the US. 95% are relatively rare, minor. 20 to 30 serious injuries occur annually, and there are about 2 to 3 deaths each year due to the fire in the OR room, operating room. About 20% fire occur in the airway. There are a lot in the upper chest, head and neck area, largely due to the oxygen escaping underneath the drapes. Here, these are reported cases across the world. This is a really global problem. We should remember the fire triangle that consists of 3 elements: ignition source, oxidizer, fuel. Ignition sources, which can be electrosurgical units for 70% or laser for 10%, and other surgical devices such as fiber optic light sources. Electrosurgical devices should never be activated when the active electrode is in the field, should be kept in its holster, and never be placed on the patient's chest and the face and the groin areas. Light cables should be connected before the source is activated, and should subsequently be placed on the standby before disconnection or placing the scope onto the surgical drape. In terms of oxidizers, such as oxygen and nitrous oxide, minimize use of open oxygen, keep oxygen concentration below 30%. When performing the tracheostomy, you may even have FiO2 turned down to 30%. But when you enter the trachea with electrosurgery, you could potentially cause an airway fire. This must be prevented. Having a fuel such as drapes and alcohol-based preps. Alcohol-based prep caused 4% of the fires. It is not negligible. Dry before draping and be aware of pooled alcohol prep before starting cases. Understanding these factors and communicating within the team are key to prevention. What to do when it occurs. Stop flow of or oxygen. When encountering an airway fire, remove ET tube and pour saline in the airway. Immediately remove the burning and burned materials from patient. Extinguish the fire on burning materials using saline or saline gases. And lastly, care for the patient. Quick video here. This video shows how to act when an oral fire occurs. The response really requires team efforts. The action should be done simultaneously and quickly in practice. We all remember the priority and order of these actions. Easy to say, but hard to remember. There's a VL training module, and you can also do in situ simulation training. The next topic is surgical smoke, also known as surgical plume, aerosol, vapor, even mist generated by ultrasonic seals. What is surgical smoke? Surgical energy devices generate smoke, which contains various fine particles, even like invisible, visible ones, such as water, chemicals, volatile organic compounds, bacteria, viruses, and malignant cells, resulting in potential health hazards for patient and the surgical teams. Surgical smoke produced by laser is composed of 95% water and 5% of other particles. More than 150 chemicals and the toxic substances have been identified in the surgical smoke. And the particles in surgical smoke generated are very small and within the respirable range. These particles can reach deep region of the lung. There are also cumulative risks for surgical teams. From the literatures, electrosurgery generates the smallest particle, smaller than 0.1 micron. Laser tissue ablation creates a bit larger particle, approximately 0.3 micron. Ultrasonic scalpels created the largest particle, 0.35 to 6.5 micron. However, the study used a particle counter that only collected the information of the particle size of that range. In addition, in this study, surgical smoke only generated by bone saw devices were analyzed. Actually, the evidence of surgical smoke generated by ultrasonic seals is scant. In general, these particles travel greater distance up to 100 centimeters. The closer you are, the more surgical smoke you will inhale. The risk of smoke exposure depends on the OR airflow systems, surgical techniques, type of energy devices, how to use the devices, target organs, etc. Limited data are available on surgical smoke generated by advanced energy devices such as ultrasonic seals and vessel sealing systems. We conducted a study and recently published in Annals of Surgery showing that advanced energy devices consistently generated surgical smoke ranging from 0.1 to 10 micrometer with greater concentration in the 0.1 to 0.3 micron zone. We didn't find significant differences between the electrosurgery and the advanced devices and within advanced devices. Here are major symptoms of surgical smoke: cough, bronchitis, asthma, COPD, inflammation of the eyes, watering eyes, headache, nausea, dizziness. There are also known mutagenic or carcinogenic effects. Oral staff can explain fatigue, skin irritation, and allergies. There are risks to the patients in MIS procedures. The level of toxic substances were elevated during lap cholecystectomy. In terms of infectious agents, the previous research showed that there are viable bacteria and viruses in the smoke. Theoretically, surgical smoke is more likely to contain the viable agent when large and low temperature particles are generated. However, in the previous study, only bone cutting devices and wound irrigation jet devices have been studied. So we don't really know the potential risk of advanced energy devices. As the particle size of SARS-CoV-2 ranges from 0.06 to 0.14 micron, theoretically airborne particle in surgical smoke may contain the virus. However, no specific test exists to evaluate the biological activity of virus DNA detected in surgical smoke, making us difficult to understand the actual risk. There is no current evidence to demonstrate a viable COVID-19 virus in the intercorporeal gas during the MIS procedures. There are different ways to mitigate the risk of surgical smoke. We were going to talk about surgical masks and the smoke evacuation systems. The operating team should wear appropriate PPEs. However, as you can see here, even if wearing a surgical mask, small particle can be easily inhaled. A surgical mask is a loose-fitting face mask intended to prevent the release of potential contaminants from us into the surgical field. Using smoke evacuation devices would be the most effective way to mitigate the risk of exposure. A number of smoke evacuators exist in the market. The device contained of 3 main features: capture devices, vacuum system, and filtration. Place capture devices ideally within 5 centimeters. We should evacuate the smoke as close to the site where the smoke is generated as possible. Select the vacuum systems that have stronger sucking power. Use multiple filters, including an ULPR filter, ultra low penetration air filter, to capture the very, very small invisible particles. There are devices that can be used in MIS procedures by connecting the tube to the port. If you don't have smoke evacuation systems, you can use wall suction instead. However, using the wall suction can evacuate some amount of the smoke. I would say that the ability of evacuation is limited due to the lower sucking power of wall suction. During the MIS procedure, we might lose visibility in the surgical field due to the surgical smoke, resulting in potential delay of the procedure or unintended injuries. Some of the devices are designed for endoscopic surgery. These devices allow the surgeon to insufflate the CO2 and evacuate gas and the surgical smoke simultaneously. This is the lowest, low-cost and effective method in lap surgery using a ventilation machine filter reported in Annals of Surgery. This is just an idea of making an inexpensive inline filter system using a 3D printer, collaborating with Kotobuki Medical Company. If you don't have these high-spec filters, then use a piece of surgical mask as a filter. Here, as you can see, a significant difference between no evacuation and using an evacuation device. You can see how effective a smoke evacuation device is. It's a huge difference. Because of the COVID-19 pandemic, the risk of the virus transmission has become a significant concern in surgical communities. Most international guidelines have advised against lap surgery and using evacuation devices. This paper also stated that the risk of lap surgery is higher than traditional open surgery. However, the evidence is scant on this topic, and considering avoiding lap surgery may be theoretical. The other reports speculated that lap procedures might actually reduce the risk of smoke exposure when compared to the open procedure due to the closed and regulated abdominal environment, which can act as a barrier and containment entity. Here are recommendations when performing lap surgery in the era of COVID-19. Incisions for ports should be as small as possible. CO2 pressure should be kept to a minimum. A smoke evacuation system should be used. All gases should be evacuated before closure, trocar removal, specimen extraction, or convention to open. Lastly, let me introduce FUSE, Fundamental Use of Surgical Energy, developed by SENSOR, the Society of American Gastrointestinal Endoscopic Surgery. FUSE is an educational program teaching basic knowledge fundamental to the safe use of energy devices. The FUSE web-based didactics are available to everyone, free of charge. In addition, if you take an exam, you will be certified. Energy devices have changed how to do surgery. However, we have experienced adverse events that never happened before: burns, unintentional perforations, and tissue injuries and/or fires. Minimally invasive surgery is not only minimum incision surgery. we might be doing maximum invasive surgery using energy devices inside the body due to lack of sound, smell, temperatures. So we should use energy devices with the lowest possible setting and in a minimal invasive way to prevent the device-related injuries and, of course, or fires. I believe that we need to change things when using energy devices to improve the patient outcomes. Thank you for your attention.
Thank you, Dr. Watanabe, for nicely wrapping up our session. So we can move on to Q&A session. So first, okay, so there has been few questions that have been answered live. Okay, so there's one question about pacemaker, that Sebastian answered. So let me just share one. Okay. Let me just share one slide here. Can you see the slide? So this is regarding what to do when there's a pacemaker. So the thing is that the electricity always travels from operating side active electrode to dispersive electrode. So if there is a pacemaker, so one way to avoid it is so where you place the dispersive electrode, so you place it as close as possible to the active electrode and not crossing the generator. So if you put the dispersive electrode as say right arm, it can go this way, so not crossing. So that will lead to some smaller damage. So if it's abdomen, like abdomen side, the dispersive electrode inside can be an answer. Yes, and there was one question about should I be worried about fluid atomization during uses of energy devices? I have not heard about it. Okay, Doctor, was that the answer from? So does anybody has
the question?
Sebastian, do you have the answer for that? The question is, should I be worried about fluid atomization during the uses of energy devices? I have not heard about it.
No, I have not, so I cannot provide you an answer, sorry.
Thank you. Dr. Watanabe, have you heard about it?
Yeah, thank you. I don't really understand the question meaning, so yeah. Sorry about that.
Yeah, okay. So we have not heard about it. So,
okay. So I think we are going to launch the MCQ.
Yes,
so
please go.
can you all please answer the MCQ online? Okay, so there goes the link for the MCQ. So please start answering. So Sasim, can we have a discussion with the rest? So let's maybe ask Dr. Kasama, what's your experience about using energy devices in Japan? We know you're a famous bariatric surgeon. So what type of energy devices do you use for your bariatric surgery?
Okay, thank you for the question. I usually use the ultrasonic mainly,
okay.
And sometimes use a monopolar for the breathing a little bit, but mainly the ultrasonic alone.
Is there a particular reason for that? Why not bipolar?
No, there is no particular reason, just for to reduce the cost, just to use one.
I see. Okay.
Instrument for the cost.
Okay, that's great. Sasim, what do you routinely use for your bariatric surgery?
So in most of our cases, I think we generally, it's like Dr. Kasama said, we used ultrasonic devices and monopolar. And we used advanced bipolar for the advanced surgery. Sometimes, like when we are doing like laparoscopic distal pancreectomy, or when we are like moving around this, like doing a lot of dissection or spleen, like splenectomy and those sort of surgeries, when there's minimum dissection, but you need a lot of you need to coagulate a lot of blood vessels, then we use advanced bipolar. The thing with the ultrasonic devices is that it allows a lot of fine dissection. It's much finer than advanced bipolar. So a lot of where I think like that's why Japanese surgeons, a lot of them, they prefer like ultrasonic devices better when given choice. The best way is if you can use the both.
Yeah.
But, it's expensive, so.
So I think most of the questions has been answered already.
There is
are in the chat box. Yeah.
There is one question like how important is it to evacuate smoke in laparoscopic surgery?
Yeah.
Okay, Dr. Watanabe, you just gave the lecture on smoke.
Thank you for your question. It's hard to answer this question because it's important, but how important, it's very hard to answer. So I don't have a real critical answer of this question, but it's important. I would say. Yeah. Sorry about that.
And Dr. Seki has a question directly to you. He asks, okay, like, surgeons have long performed numerous MIS procedures worldwide without paying much attention to surgical smoke. I'm curious to know if actual health harms have been reported or not.
Yes, there are some reports in the scientific paper. There's one like a cardiac event. It's occurred to the OR staff nurse. That this is reported in a New England Journal of Medicine long time ago.
So,
and the OR staff have a higher chance to have like respiratory symptoms compared to the other, the nurses.
Yeah, I think the other thing.
Go ahead.
Yeah, I think the other thing is not how important is it to evacuate smoke in laparoscopic surgery, is basically how effectively we should do the smoke evacuation. And I think Dr. Watanabe mentioned about the ULPA filters and all that. So the surgical smoke does have significant health hazards. So we should evacuate it effectively using proper methods rather than just open up the port of pot to just let the smoke come out. So we all inhale during the operation theater.
Yeah. Let me add to that, like what Sujit said. Like, I think it's actually much more harmful if you just open up the port. It's much more harmful than open surgery where you are just, because you are having it in a pressurized abdomen and you are like letting it through a small port. So it's so it just like jets out. So it has much more potential to reach much further and more harm and get more insights. So I think best way is to have the smoke evacuation system. But if you do not have, do not open the ports to let the smoke out. Like, that's the worst thing you can do.
Yeah, Sasim, there's a question for you. How about lymphatic sealing regarding advanced bipolar versus ultrasonic devices? Which one most effective?
Okay, so I think obviously advanced bipolar are, I think, much more effective in thermal sealing. And with ultrasonic device, it's like advanced bipolar has become much more like machine dependent. So you just grab the tissue and press the button and the machine will do the rest. With the ultrasonic, it's still a lot of, depends on the user, like how much tissue you are catching, how much tension have you applied, if you are like how much squeezing, like, and like which button you are pressing. So if you, so in that manner, so if you use it properly and everything, you can have maybe similar result. But if you just do it like a random test, like the advanced bipolar will probably come on, it will have a better effect.
I totally agree with what Sasim said. Yeah, it's true.
There's another question. What's your experience to use the advanced bipolar forceps in multiple locations?
So do you, I think he may, like, this means like reusing the disposable instruments.
Yeah, I think so.
Okay, there are some, but okay, so I think we cannot recommend that. Yeah. Because I like so we cannot recommend that. It is meant to for like a reusable, there are reusable instruments that if you are worrying about the cost, there are reusable instruments that you can use. And but if you want to effectiveness, I think it's best to use it as recommended once, if you are using the disposable ones.
Yeah, Sebastian, you want to mention something about the reusable bipolar instruments? I think Irby has a couple of them. Yeah.
I agree. So if you're using single-use instruments, that's what their name gives away. It's single-use really, and also the insulation that the instruments use is only well planned and designed for not multiple uses but single use. And if you rather want to use bipolar instruments on a frequent basis and then use instruments that are reprocessable. I think that is something also this study that was shown during the session also showed, with the number of reprocessable instruments that have a destruction in their insulation is of course due to the reprocessing cycles, and therefore over time you must indeed check the insulation also with these instruments. Thank you.
That's the important thing, like Sebastian pointed out. So if you are using these instruments, like it's prone to have insulation failure. So, and then it may work properly on the operating side, but you may have the injury somewhere else. So we need to be careful on that. Okay, so.
Okay. So just another reminder for those for our participants. So please do complete the MCQ test. So Dr. Marlu, who is one of the MIS surgeons from Philippines, she has helped us compile the MCQ. So please do complete the MCQs. And any experience about energy-related complications? So maybe Prof. Lamanto or Prof. Sakai can enlighten about some of your experience about energy-related complications.
Hi, I'm Sakai. May I?
Yes.
Yes, Prof.
I have when I am started the laparoscopic surgery, I have several times of the intestinal damage by the spreading of heat. That is the worst experience.
Yeah, me too. Other than bowel injury, I have a few scary rupture of vessel, especially short gastric vessel for the lateral spreading, because sometimes especially the bipolar, they can reach very high temperature, about 180, 170, and they may injure the tunica of the artery, and after a while, if the high pressure, they burst up, and it's quite scary to see a big flow of blood in front of you, obscuring the view. Yeah, energy, I think as the Watanabe, Sujit, and Sasim's nicely show, need to be used carefully. And especially when you use high temperature energy, they use high temperature like ultrasonic or advanced bipolar. Avoid to touch for the next 2-3 seconds any organ nearby, because let them cool down before you regrab again.
Okay, thanks, Prof. There's one more question, I think one last question. Could you explain us what cavitation is when using ultrasonic shears?
So it's cavitation, I think, is one of the most poorly understood mechanism of ultrasonic shears. It's actually micro bubbles, like a vaporization that comes due to the constant back and forth movement of the active jaw, and like heating of the tissue, like the water content inside the cells, creating micro bubbles. I think like that spraying is like during the surgery or not, but mostly it's just it's the thing that comes out and like creates this mist and vapor. That's how I've understood it. Dr. Watanabe, you have anything to add on that one?
Not really. You're right.
Cavitation is, imagine that you have a boat at the propeller, the movement of the propeller. So practically is when, you know, the ultrasonic blade can vibrate up to 150,000 per second. So this vibration and the effect on the water content in the tissue create a vaporization of the tissue. That's why even in a boat propeller, the cavitation of the propeller is called cavitation. So it's a spinning effect of the speed of the vibration plus the water. It's also very useful, the smoke evacuator, because why you aspirate all this cavitation smoke that is not harmful like this proper smoke, improve your vision. Otherwise the camera get dirty because the water will dirty. I'm sure Kasama knows when they do bariatric surgery with all the ultrasonic cavitation, it's very annoying.
Yeah, that's true. Sometimes that the cavitation causes the leakage of the shrimp gastrectomy, so that we are very afraid of doing this. So we have the care must be taken for the cavitation.
It can.
Go ahead.
Yeah. Please go ahead, Dr. Watanabe.
Most injuries are related to the ultrasonic sears is not due to like a cavitation. I believe that like a kind of like a drilling, the touching the tissue, the active blade.
So we are just like, that's what I wanted to see. So we are just, the active blade is constantly hitting the tissue, so at the tip. So that is generally a lot of times, I think that causes injury more than like cavitation is basically vapors, micro bubbles. So it's a mess. So like it's poor, like I said, it's poorly understood. So the injury may be due to the drilling effect more than the cavitation. So in any case, don't have important structures at the tip of the ultrasonic scissors. I think that's way to avoid it. There is one question, one more question. What kind of ingenuity do you do to clean the tip of devices quickly during the surgery? Sujit, how do you clean up the tip of the devices?
So if it's monopolar and bipolar, we do have this thing called surgigauze. So in different countries, they use different words. So we call it surgigauze in Singapore. It's basically a material that can help to wipe off the carbon that is deposited, because too much carbon can give rise to issues in bipolar instruments, especially. So for ultrasonic shears, we use a wet gauze to wipe off the damaged tissue or leftover tissue, so that it can have a proper seal up and proper action on tissue. Yeah.
Okay, Dr. Kasama, how do you clean in your institute?
In my institute, just wipe with a sponge.
I think that's also a very effective way.
Right.
Yeah. Dr. Sakai, do you use how do you clean the tip of the jaws?
Just with a gouge.
Simple and cheap.
Yeah.
Wet gauze is like it works most of the time.
Wet gauge.
Yeah, simple and cheap, and also for ultrasonic scissors, if it's not working properly, you can always activate it inside the water. It also helps clean it. So after, especially in long operations, so if it's like taking 2, 3, 4, 5 hours, so and then you can generally use this one too. Okay, so that's the question we have.
So if there's no other questions, Prof. Sakai, Prof. Lomanto, shall we conclude for today?
Yes, I think we can conclude. Thank you, everybody. Thank you very much. Thank you, Kazu, for organizing. Thank you, Suzuki for for coming.
Thank you very much.
Together with
I could
Basim.
remember the principles of the energy device. Thank you very much.
Thank you for getting us the opportunity to do this webinar. So, okay, so Professor Lomanto, Dr. Kasama, if you can give the closing comments, then we can close.
Yeah. Sakai, you go ahead. Or Kazu.
Well, I just finished. So,
then Kazu, we give the microphone to Kazu.
Oh, thank you,
please.
David, for giving me the opportunity to have some comment regarding this webinar. So actually, this is the first ELSA and the JSES joint webinar. It is a great opportunity for young surgeons in Japan to participate in the international event in this COVID-19 pandemic era. So that it's a great opportunity for all of us. And I want many young surgeons to aim Asia and to be the international surgeon from now on. Thank you, David, and thank you, Sudhis, and thank you other panelists and speakers for this great event.
Thank you.
Thank you, and bye-bye. Thank you, bye-bye.
Thank you so much.
Bye.
Bye-bye. Good night.
Thanks.